constants. The c's are constants, not variables. They are constants, not variables. And then x is the variable, and a is also going to be a constant. So this is the general form of a power series. Similar-ish to what polynomials look like, but the idea is you have ascending powers. So is there a common ratio?
Yes.
They're not really, because if the constants were the same, there would be a constant ratio, right? But the constants could mess up the ratio. But the idea is what's happening to the power of x minus a at every point? It changes by 1. That's it. But the leading coefficients could ruin the geometric nature of it. Are there geometric power series? Absolutely. Like what happens if c is 1? Sure. If all the c's are the same, great. So here's the thing. This has x in it. We could write out a bunch of terms. Like we could make up values for c. Anybody know how you say that out loud? C what? C naught. N-A-U-G-H-T. C naught. Nothing. C0. C0 or C naught. C1. C2. We could just put values in, right? We could write a power series. This is the general form of it. But in the power series, as this is written, there's an x in it. We can plug in something for c and we can plug in something for a, but x is in the power series. We've looked at series. Some series converge, some series diverge. We're going to write power series, and what we're going to figure out is for which x values does it converge, and for which x values does it diverge. That's what we're going to be looking at. We're going to be looking at intervals of convergence. Basically, we're going to find pieces of the domain where those x values cause the power series to converge to different things, but it converges to different things, and where it causes it to blow up. Where it causes it to blow up. And that's what that second blue box says. It says for a fixed value x, if the sequence of partial sums converges, that is, this limit equals L, then we say the power series converges to L. A power series may converge for some values, but not for others, and not for others. So for example, here's a power series right here. And if x is equal to -1, what do we do with that -1? We just plug it in. That's all we do. We're just plugging it in and seeing what it looks like. So what does this look like? If x is equal to 1, we'd have the sum from n equals 0 to infinity of -1 to the what? N over 2 to the n, right? What is this? It's an alternating what?
Alternating series?
It's an alternating series. So if we were to write out, let's just write out the terms. And it starts at n equals what, by the way? N equals 0, right? So if we plug in 0, what's the first term? 1. And what's the second term going to be? -1/2, and then plus what? 1/4 minus 1/8, etc., right? What is that? What kind of series is that? What kind of series is that? Come on.
It's geometric.
It is geometric.
And
it's geometric with ratio what? And we know that the absolute value of 1/2 is less than 1, so therefore this must what? Converge. We also know it converges by another thing, the alternating convergence, series convergence test. Is this an alternating series? Is it going to 0?
Yes.
Therefore, does it converge? Yes. So when x is -1, this power series converges. The power series is when its x is in there. What about 3? Let's plug in 3. We have sum n equals 0 to infinity of 3 to the n over 2 to the n. What is this? N equals 0 to infinity of what? 3 over 2 to the n?
Yes.
This is a geometric series, right?
Mm-hmm.
What does r equal?
3 over 2.
3 over 2. But 3 over 2 is greater than 1, therefore it diverges. So for some x values it might converge, for some it might diverge. Guess what? There are power series where no matter what the x is, it definitely always diverges, and then there are some where it definitely always converges. So you're going to get a power series, and there's 4 classifications of answers. Either it converges everywhere, or it diverges everywhere, or some places it converges and some places it diverges. That's 3 classes, I guess. 3 classes. Okay, so sometimes, though, we might not be given the nice notation. This was nice notation right here. It's great to have that. That's the explicit definition. This right here is a power series, but is this an explicit definition? Basically, I want you to use summation notation. How do we write that in summation notation? So what's the a value, by the way, on this? What's the a value? What are you subtracting from all the x values? 2. So this thing is going to be the sum n equals, where do you want to start n? N is 1 or 0. What do you want to start it at? They seem to like 0 on these power series, so let's start at 0. So if we start at n equals 0, it's going to be x minus a to the what power? I think it's n plus 4. Is it, well, 4, then 6, then 8, then 10, right? So what is it going to be? If we're starting at 0, what's the power of x minus a going to be? You could write it as, I don't know, 2 times n plus 2. right? It's double 2 up from it. Are we okay with that?
Mm-hmm.
And what is it over? 2 times what? N plus 2. It's the same. Oh, is it not? Oh, it's not the same, is it, huh?
Yeah,
So it's 4, 9. Oh, what? They're squares, right?
yeah.
So N plus 2 what? Squared. Nice. Oh, and then it's also alternating. And the first one's positive, right? So it's just to the n. That's why starting at 0 is kind of nice. You don't have to write the n minus 1 if it starts positive. Hey, so this is find an expression for the general term of the series and use this to write the series using summation notation. This is it. There it is. You just built it. Awesome. Are there a lot of places where you can kind of get it wrong? Yep. Forget the alternating, start it in the wrong place, start the index at the wrong place, but you need to build it. You'll need this expression because we're going to do certain algebraic manipulations that involve using the explicit form of this. The explicit form of this. Okay, so let's look at a general power series here. Let's look at this one right here. Is that a power series? Sure, looks like it. Could someone just tell me what the summation notation is for this one? What's the summation notation for this one? N equals 0 to infinity of x minus 1 over what? X minus 1 over what? N plus 1 to the what power? N plus 1 power. And it's alternating. Oh, look at that. Nice. Okay. Fantastic. So here's the thing. If you plug in an x value, let's say we plugged in 1, what happens if you plug in 1? What do all the terms become if you plug in 1? What'd you say? They become 0, 0, 0, 0, 0, 0. So does that converge when x is 1? What's the sum of the series when x is 1? 0. Does it converge? Yes, it converges to 0. So we know when we plug in 1 for x, what do we get out? 0. Hey, that's nice. Fantastic. Okay, so take a look at this graph. Let's take a look at what this is right here. Let's see if we can figure what the relationship is here, right? If you plug in 0, what do you end up with? You end up with -1 minus a half minus a third minus what? What is that? That's opposite the harmonic. What does that do? Diverges. So it looks like at 0 it diverges, but maybe it's everything up to but not including 0, right? So we're getting an idea here that you could plug in individual x values, but how many x values exist between 0 and 2? And can you plug in all of them? No, you can't. So we need a better test for that. But it looks like for 0, this endpoint doesn't converge at 0. When x is 0, does this converge? We just said
no. When
x is 0, it's the opposite of the harmonic, which definitely what?
Diverges.
What about when it's 1? We said that at the beginning. What happens when you plug in 1?
It converges. It
does converge. So we know that at 0 it doesn't converge, but at 1 it does. And we kind of think that everywhere in between it does. So we think, what's our guess for the interval of convergence? What's our guess? Not 0, but goes all the way and including what?
1.
So this is our guess for the interval of convergence. But here's the thing. That's a hand-waving way to do this and a terrible handwriting. I'm going to write that in real English here. But that was just a hand-wavy part of it. We looked at a graph and we're like, oh, it looks like it does. How do we do it? How do we do it? How do we do it? So there's a lot of text here. I don't want to put it all up there. Just this looks similar to what? What does this look similar to? It looks similar to the ratio test, right? Yeah. It looks very, very, very similar to the ratio test. So what are you doing here? You're taking the limit as n goes to infinity of the next term over the current term. And remember how those constants were up front? This is just the power series definition that we're looking at. That's all it is. Do you have lots of experience doing limits? Everybody raise your hand. Everybody raise your hand. Erica, raise your hand. Do you have lots of experience doing limits? Oh, look, you're all raising your hand. Excellent. Okay, good. So here is the ratio test that we're going to be working with. Here it is, right here. I'm going to run the ratio test. We think the guess is 0 to 1. Let's see if we can get an answer that matches that. This is not the explicit formula, right? What was the explicit formula? I think I wrote it right there. What was it? This thing, right? So let me write that a little prettier. So what was that? It was the sum from n equals 0 to infinity of what? -1 to the n, and it was x minus 1 to the n over what? n plus 1, right? So that's the nth term.
It's x minus 1 to, wait, to n plus 1.
Yeah. To the n plus, oh, thank you. Yes, that is very important. Okay, so this right here that's the an term, right? correct? So we need to do what limit? We're going to do the limit as n goes to infinity. We need to do the next one. What's the next term going to be? Negative 1 to the n plus 1, x minus 1 to the n plus 2 over n plus 2 all over negative 1 to the n, x minus 1 to the n plus 1 all over. So this is key. There's an absolute value around it. Do you remember that as part of the definition? Okay, that absolute value is really helpful because what does it immediately get rid of for us? Well, the negative one to the ends, right? Because they just become what? Positive. They become 1, right? So let's rewrite this and flip it over. Let's rewrite this and flip it over. So what does this become? The limit as n goes to infinity of x minus 1 to the n plus 2 over what? N plus 2 times over plus 1, right? Does something cancel there? Yeah, so this goes away, getting rid of everything but that 1 power. So what are you left with? The limit as n goes to infinity of what? X minus 1 times all over n plus 2. Do you agree? Are you okay with that? Are we okay with that? As n goes to infinity, what happens to this? As n goes to infinity, that green bubble turns into what? 1. So what's the answer to this limit? What is the limit on this one? What is it? What's the limit? X minus 1 is the limit. So we go down to this blue box that we just got, which is great stuff. Super cool, if I can actually get the right size. And what does it say?
Yeah.
What does it say? It converges if L is less than 1. Does everybody see part 1 right here?
Yeah.
What did we find out? We just found out that the limit was what? So x minus 1 must be less than 1 for it to converge. So therefore x minus 1 has to be less than 1 or greater than what?
Negative 1.
So you add 1, what do you get?
You get 2 on that side and 0 on the
0 on that side. And is that what we suspected it would be? We really did. The thing we haven't tested that we're going to test now are the endpoints, which we did already. The endpoint is x equals 0, and there's another endpoint 2. But let's go back to the original series.
And that was the interval, right?
That was the interval. That was the interval from 0 to 2. So let's go back to the original series, which was right here. What happened when we plugged in 0? What did we get? We got the negative harmonic. So what is that? It's not part of the convergence, right?
So it's not.
So it's definitely this, right? But then when you plug in 2, what do you get? What do you get when you plug in 2? I'm sorry, I can't bounce it. What happens when you plug in 2? When x is 2, what do you get? 1 minus what? Plus a third minus what? Minus plus a fifth. And what is that? The alternating harmonic. Does that converge?
Yes.
Yes. That converges. So what's the interval of convergence going to be?
Less than or equal to.
Yes. So after you find the interval, you have to test, if I can actually write it out, test the what? Endpoints. Hey, was our guess pretty good? Guess was pretty good. Our guess was pretty good. But we just proved it, and that's all because of this, the ratio test. So if it converges, the limit has to be less than 1, and you're just asking your question, what are the x values that make it less than 1? And then you have to test the endpoints by specifically plugging in those endpoints into the original power series. Yes, Seema?
This is all assuming it converges.
This
I got that x minus 1 is less than 1.
No, for it to converge, it has to be true. To converge, that must be true. To converge, I can't write. To converge, this has to be true, right?
Yeah.
So what does this, oh, how did I get the,
Absolute value.
it's absolute value, I'm sorry. There's
okay.
there's an absolute value. I'm so sorry. I didn't write the absolute.
I got the 2.
Yeah,
The one-
remember the absolute value when we did this it's just along for the ride.
Okay, so
It's-
when you get the limit, it's the absolute.
Yes,
value.
the absolute values were in the entire time, right?
Right.
Sorry, it's this, my mistake. Yeah, that's where the negative 1 came from.
Gotcha.
Okay. So we have the ratio test, and this is what it really comes out to. Method for computing the interval of convergence here. So you do it. This is what you get. Let me just stop this. If we're going to find out if this power series converges, we first need to write the explicit definition. Can you tell me what the explicit definition is, Tomas? What's the explicit?
X to the n. Oh, n equals 0 to infinity.
N equals 0 to infinity, yep.
Of x to the n
Mm-hmm.
over
What?
factorial.
Over n factorial. Exactly. Yes. That is 100% correct. Good job. So now we run the what test? We run the ratio test. So I'm going to just skip some of the algebra a little bit. I think you can handle it. It's going to be the limit as n goes to infinity of the next term, right? Are you with me so far? Divided by the current term. So what's the current term going to be? I'm flipping it over because you're dividing, right? Are you okay with that?
Sure.
Now we just need to be careful about what we need to be very careful about what we cancel. We need to be very careful about what we cancel. When I cancel this, what's left on the bottom? Yes. What's left on bottom is n plus 1, right? We just got rid of the rest of the terms. This goes away, leaving you with what on top? X. Okay. X is a finite number. Like x would be a fixed number. You fix x, but n always goes to what? So what is this limit? 0. Is that so what does this tell us? It is always less than 1. So this thing is going to what? Always converge. So it converges for what? For all x values. It converges for all x values. It converges for all of them. No matter what x value you put in there, it always converges. That kind of speaks to the power of what operation on there. Basically, that's telling us that what operation is super powerful. Factorial is freaking powerful, everybody, right? It's huge. It's really, 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 really powerful. Are you okay with that one? Does that make sense, everybody? So what's the radius of convergence on that one? What's the radius? Infinity, because it converges everywhere. Everywhere. Nice. Okay, so I think we just did that one, right?
Yeah.
We did one very similar to that one.
Yeah.
Did we do that one exactly?
It looks very, very similar.
Looks very similar. So if we were going to do this one, I think we did it, right? Let's just check it.
Yeah, we just did.
I think we
n
did.
equals 0 instead of n equals
Well, 1, yeah, I think we did the same thing. Yep. Nice. Very cool. Oh, and by the way, this should have been a 2 right there, sorry. Because it goes all the way to what? That number is 2, and this is 0. Okay. Okay, so let's do another. We just did that one. Yay, very exciting, very exciting, very exciting. So you want to do a more entertaining one? Let's do, I want a good one here. Here, go to the board, everybody. We already did the endpoints. Yay! Try that one right there. Yeah, don't write on the projection, remember, long. And you're working with somebody else? Everybody's in pairs, everybody. There should be pairs. Pairs, everybody.
So let's define this recursion first off. So it's the summation.
So we'll start with 0.
Yeah, it's 2, so n is equal to 0
Oh, it's already got it.
to infinity. So we have 0 to the power. So it's 2. It's 2x. 2 to the power. It's 2 to the power n multiplied by x to the power n. No, hold on. It's not that, because that's 1, 2. That's 3. It's 2. It's not that. I see.
Now we up. Now
It's like 2. And this should be. When that thing happens, it's usually 2n plus 2. Like, I've gotten used to these patterns. Let me look at this. Or is it 2? This is my go. Look at this. So our second one.
I liked what I saw. You immediately dove in and you wrote the explicit formula. And the explicit formula was n equals 0 to infinity of what? 2 to the 2n, x to the 2n, right? So then you guys, is that right? Yeah, I think so. Limit as n goes to infinity of 2 to the 2, what was it? N plus 1, x to the 2 times n plus 1, all over what? 2 to the 2n, x to the 2n. So when you cancel this, what do you end up with as your limit here? You end up with 4x squared, correct? And the absolute value of that needs to be less than what? So the absolute value of this needs to be less than 1, but 4x squared is always positive, right? 4 is always positive, x squared is always positive, so you're just solving this. So that's this, correct? So then you have to be really careful about this. What numbers solve this? What numbers make this true? x is going to be between a half and what? Negative 1/2. But you're not quite done because you just found the interval of convergence mostly. What do you have to test? Test endpoints. And I stopped you before you did it because I just wanted to make sure we did it all together. How do you test endpoints? You take negative 1/2 and a positive 1/2 and you plug it in here. So if x is equal to, let's say, a half on this one, what do you end up with? 1 plus 2 squared times 1/2 squared, right? Plus 2 to the 4th times 1/2 to the 4th. So what is that? 1 plus what?
1.
Plus 1. Is that going to converge? So when x is equal to a half, it does not converge, right? So we're okay on that end. What about negative 1/2? Is negative 1/2 going to change anything about this? All the powers are what?
Even.
All these powers are even, right? So when we plug in negative 1/2, does that change anything?
No.
No, it's always even. So we checked both sides. They work. So what is the interval of convergence? Is negative 1/2 to 1/2. What's the radius of convergence?
1/2.
Is 1/2. Yep. The radius of convergence is 1/2. That's correct. You test the endpoints. That right there is the most common thing. And I can guarantee you're going to be forced to test the endpoints because how are they going to do the multiple choice on this on the AP test? They're going to be like, what's the interval of convergence? And the answers are going to be like this. Do, 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 do. They're literally going to give you things like that. I'm not kidding. And you're going to be like, yes, it's 0 to 3. And then you look at the answer and you're like, I've just eliminated one answer. You have to test the endpoints. You have to test them.